Resonant pulse commutation circuit. Resonant pulse commutation is a type of the forced commutation itself. Initially, the capacitor is charged with minus V0 voltage and the polarities are shown in the figure, and thyristor T1 is carrying a load current of Im. Now, when the commutation thyristor T2 is fired, the resonant circuit is formed between L, C, T1 and T2, and the resonant current is given by I of t equals to V0 square root of C by L sine omega mt. This can be equal to Ip sine omega mt, where Ip is equals to V0 square root of root C by L is also known as permissible value of resonant current. And the capacitor voltage Vc at t is given by minus V0 cos omega mt. Due to this resonant current, the forward current of thyristor T1 is reduced to 0 at t equals to T1. When the resonant current equals to the load current Im, the time taken T1 can be found by using the condition that I at t equals to T1 equals to Im. Now substitute this in the above equation. We're going to get T1 equals to root of Lc as omega m equals to 1 by root Lc sine inverse of Im divided by V0 root of L by C. The corresponding capacitor voltage is Vc at T1 equals to minus V1. This is T1, which is equals to minus V0 cos omega m of T1. After this, the current through the thyristor T1 will cease to flow and the capacitor will recharge at a rate determined by the load current Im. The capacitor will discharge from minus V1 to 0 and its voltage will then rise to DC source voltage Vs. In which case diode Dn starts conducting. This situation is similar to the circuit of self-commutation. Please go through the topic of self-commutation. The link is given in the description below. After this, energy stored in the inductor L due to the peak load current of Im is transferred to this capacitor, causing it to overcharge. Now the capacitor voltage reaches V0. This is T of time. This is charging time. The capacitor. This is T0. Now at T1, the current reached Im. Here Dm is on. Here T2 is on. Now the capacitor voltage reached V0. Capacitor voltage, that is Vc, at t equals to T1 plus T of plus Tt plus T0 is given by Vs plus Im square root of L by C, which equals to V0. And this can be reversed by firing the thyristor T3 as we've seen in the self-commutation. The equivalent circuit for charging period is similar to the equivalent circuit of impulse commutation, and the link is given below. Please go through the impulse commutation process. Then the circuit turn off time T off is given by C V1 by Im. Now let us define a parameter X, which is the ratio of peak resonant current Ip to the peak load current Im, equals to Ip by Im, which equals to V0 by Im root C by L. To reduce the forward current of T1 to 0, the value of X must be greater than 1. In practice, the value of L and C are chosen so that the X value equals to 1.5. The value of T1 is small and D1 is approximately equals to V0. This is T1 and this is T2. At T2, the capacitor current falls to the load current Im. During the time Tc, the capacitor C discharges and charges to supply voltage Vs. During the time T0, the energy stored in the inductor L is returned to the capacitor C, causing the capacitor to overcharge with respect to the supply voltage Vs. Due to the fact that resonant pulse of current is used to reduce the forward current of the thyristor T1 to 0, this type of commutation is known as current commutation. The circuit turn off time T off is also dependent on the load current Im. The discharge of capacitor voltage can be accelerated by connecting diode D2 as shown. Once the current of the thyristor T1 is reduced to 0, the reverse voltage appears across the T1 is the forward voltage drop of diode D2, which is small. This will take the thyristor recovery process slow, and it would be necessary to provide longer reverse bias time than dot if the diode D2 were not present. This is the circuit for resonant pulse commutation with the accelerating diode, and these are the waveforms for accelerating diode. For the given resonant pulse circuit, determine the circuit turn of time T off if Im is 250 amps and second case 50 amps. And the given C equals to 30 microfarad, L equal to 4 microhenries and V naught equals to 200. Now we need to find out the T off, which equals to C V1 divided by Im. We need to find out V1 minus V naught cos omega m of T1, and T1 can be calculated by using the formula root LC sine inverse of Im by V naught root L by C, and omega m equals to 1 by root LC. By using these formulas, let us find out the first case where Im equals to 250 amps. Now, let us find out the value of T1. Square root of 4 into 30 sine inverse of 250 divided by 200 square root of 4 by 30 equals to 5.192 microseconds. Now, omega m equals to 1 by square root of 4 into 30, that equals to 91,287.1 radians per second. Omega m T1 equals to, when you multiply these two, you'll be getting 0.474 radians. V1 equals to minus 200 cos of 0.474 radians, which equals to 177.95 volts. The P off equals to C is 30 microfarads multiplied by 177.95 divided by Im is first case 250. That equals to 21.35 microseconds. Repeat the same process for Im equals to 50 amps. Then you are going to get the T of time equals to 119.5 microseconds, and we know that the T off is inversely proportional to the Im. As the load current decreases, the turning off time will increase. Please try to solve this for 50 amps